calculate the pH of a half liter of a buffer solution composed of 0.50 molar formic acid and 0.70 molar sodium formate before and after adding 10 milliliters of 1 molar HCl. Okay, before and after. We'll do the before, then we'll do the after. So before is just calculate the pH of a buffer. The after is after I've invaded it with some strong acid, because you recognize HCl as strong. Let's contemplate sig figs so we don't have to contemplate them again. 3, 2, 2, 3, 3, 2 it is. So 2 sig figs are limiting me, therefore I need 2 decimal places on any pHs or POHs. I just like to write that down. On pH, I'll put it that way so it makes sense to you when you look at it later. Alright, so let's do the before. Caution, easy math approaching. H plus, this is what you have to memorize, equals Ka times the ratio of weak acid to weak base. And that is equal to what I told you, 1.8 times 10 to the minus 4. Or you've worked some other problem that has gotten you to this point. Alright, so now, that's 1.8 times 10 to the negative 4. I just need this ratio. So what was the molarity of the acid and what was the molarity of the base? It's a good idea to also mark your acids and bases. So, blah, blah-ic acid. The word acid is a big old clue that that's my acid. And so it is 0.50 molar. And blah, blah, 8. You're looking, if it's an acid, you're looking for blah, blah, 8. We'll work some basic ones later, but formic acid, sodium formate, or us acid, and 8. So the 8 is like, you got a lot of polyatomic ions that end in 8. You only have memorized a handful of them. There are hundreds of thousands of them. So formate, acetate is one, acetate's one you know, propanoate, methanoate, there's loads of them. So we just have you do the most common. So basically this is the salt, and the fact it has sodium in front of it, or potassium, or anything soluble like ammonium, is also a big hint. So here's my base. That's my weak base. So 0.70 molar, and we'll get what that equals. So are you ready? 1.8 second EE minus 4 times, open a paren, 0.5 times, oh, not times, divided by. Oh, goodness. Divided by. That's better. 0.7. I know you beat me. 1.28, blah, 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 blah. Okay, let's go with 1.29 times 10 to the minus 4. That's what my H plus equals. So therefore pH is the negative log of that number. Kids always ask me, what do I have to write down? I would write it down this way, just like you see it here. That's all I would write down. You could probably even skip this bit right here, if you can see my little circling, my Ka stuff. But it wouldn't hurt you to write it all down so you can make sure you get all of your points. It only takes an extra couple of seconds. I know you're lazy. Me too. So here comes the lazy part. Negative log. You can either go second answer or you can reach up there with your up arrow if you've got the new operating system. Enter pastes it in. Enter executes the command. 3.89. 2 decimal places? Yes. 2 decimal places. 3.89. Now, teaching moment. See that minus 4? See the fact there's a number in front of it greater than 1? If this were 1 times 10 to the minus 4 for the Ka, at this moment the pH would be hovering right around 4. The fact that it is a number greater than 1 in front means just drop down a little bit. I was expecting a pH somewhere in the neighborhood of 4, but slightly less than 4. So again, I want you like a heat-seeking missile to lock on to the exponent on Ka values and realize that if you're in the land of buffer, meaning your acid you're talking about is weak, which is the only time you're going to have Ka value anyway, right? Because we don't do Ka values for strong acids. They completely dissociate, throw you into the land of stoichiometry. The only reason you're in the land of buffers is weak. So when you see that, you lock onto that exponent and you say, okay, my pH I'm estimating is going to be in the neighborhood of that exponent, but it's not uncommon for it to be slightly lower. The larger the number in front of the times 10 to that part, the lower the pH is going to be, because the closer you're inching your way up to a power of 10, right? Because 1.8 is on a climb up to the number 10, which is going to make this 10 to the minus 3. So So I'm headed toward a pH of 3 if it were 1 times 10 to the minus 3, which is the same as 10 times 10 to the minus 4. Alright, shall we do the after? When you do the after, hear the sound of my voice loud and clear. I want you to hear the sound of my voice when you're working your homework problems too. When you add anything into a buffer, you must go directly to moles. Do not collect $200. Do not pass go. Go directly to moles. So in the after, go to moles. Go to moles. Get out of molarity. And moles is molarity times volume. So it's not a hard calculation. H plus is still equal to Ka, weak acid times the weak base concentrations. Only we're going to go to moles. So that's equal to 1.8 times 10 to the minus 4. And why can we do that? Why can we switch back and forth between moles? I know you don't trust me. It's because here we have a half a liter. So if I stay in molarity, the half liters cancel out anyway. If I just stay in moles, then all of my volumes take care of themselves. And it's actually a simpler, easier calculation. Alright, so that's still equal to that same Ka. Now, that's equal to, leave brackets. Brackets are for moles per liter. Parentheses are for anything else. Because I'm in moles, I'm going to go to parentheses. Let's do a little simple math in our heads first. We have a half a liter times 0.5 molar. So molarity times liters is 0.5 times 0.5, which is 0.25. So we have 0.25 moles. Now, I did that in my head, but let me show you what that looks like. 0.50 moles per liter times 0.500 liters. Liters cancel, and I get 0.5 times 0.5, which is 0.25 moles. I'm just going to write that up there on the above. Okay, and that's going to be one calculation. Do the same thing for your base. Can I cheat for the base? Can I go easy? 0.5 liters times 0.70 molars is 0.35 moles. Alright, now, here comes the fun part. What are we invading this with? We're invading this with HCl. Is that an acid or a base? Quit laughing. Is it an acid or a base? Right, it's an acid. So I'm going to add to the acid and subtract the exact same quantity from base in moles. So 10 milliliters is also known as 0.010 liters. 1, 2, 3, that is correct. So 0.01 times 1 is 0.01. So 0.01, 0.01. Resist the urge to get creative. Once you find out the moles, it's the same top and bottom. The tricky bit was the add plus part. So you're adding acid, so add acid. Add to the acid, subtract from the base. Do not reach for that calculator. Don't do it. We're going to do this math in our head rather than waste time punching a whole bunch of buttons that we could have just thought about for a second. This numerator now is 0.25 plus 0.01. Isn't that 0.26? This denominator is 0.35 minus 0.01. Isn't that 0.34? Now you can take your calculator. So now go get your 1.8 second EE minus 4. And multiply it, open a paren, and this is simplifying right now to 0.26 divided by 0.34. I just did all of that purple scary math kind of in my head. So 0.26 divided by 0.34. Close the paren, enter. 1.37 yada yada yada. Yada yada yada, very scientific lingo. So therefore, my H plus is equal to 1.3, I'm going to call that 8, times 10 to the negative 4. Therefore, pH is equal to negative log of 1.38 times 10 to the negative 4 is equal to negative log second answer, or go get it, grab it, paste it, execute it, either way, whatever you like, 3.86.